Yeah, thank you very much for the introduction. As she already said, my name is Raphael. I'm a software developer, entrepreneur, previous coordinator of this conference, DSF member, so on and so on. I'm very happy to be here and be speaking to you again. Sorry? Today I'll be speaking about debugging slow requests, specifically debugging slow requests that are slow in production. I will talk a lot about database issues, and I will be always using PostgreSQL as an example because it's what I know best. The ideas for the other databases are the same. Transfer them at your own peril. We're going to look at this in 3 different scenarios. The first is the scenario in which a specific view in your application is suddenly slow and you need to figure out why and what to do about it. The second is that you notice your database being overworked and using too much resources, and you want to figure out what part of your application is causing it. And the third is a short general look at performance issues that are not related to the database, which is rare but does happen. So let's start with a specific view that is slow. A customer calls you, sends you an email, complains, I click this button, it is slow. And let's work with an example. Let's build a very simple Django app with a very simple database. We have one model that is a publisher and one model that is a book. The publisher has only a name, the book gets a title, a description. We're just going to model the authors as a text field as well to keep it really simple, with a publish date and a price. And I found a data set, free data set on the internet with 100,000 books, so we have some amount of data loaded into it. So depending on what industry and type of application you work with, 100,000 rows might be a lot or nothing at all. In my day job, we deal with tables of up to a few hundred millions of rows, so 1,000 times that. So at 100,000 rows, lots of queries are still fast, even if they're not. Like even a slow query might only be a few hundred milliseconds, which might still be acceptable, but once we grow a little bigger, it might no longer be. I just didn't find a larger, suitable, simple, free data set that we could use here. So I think we've already seen and talked about the common N+1 query issue today, and I'm just going to repeat it very quickly so we can move on to the more interesting stuff. Suppose we have a template snippet where we iterate over a list of books, and for every book we print the title, the publisher name, and the year, like a very short citation. What this will do behind the scenes is run a select query for the books, and then another select query for every one of the books to fetch the publisher. And obviously, that is not the most efficient way to do it. And we've already heard about select related today, and prefetch related, and I think probably 80% of the people in the room know these. For beginners, it's sometimes a little bit hard to understand when to use which of the two. My general rule of thumb is, well, you need to use prefetch related for many-to-many relations. And I also find myself using prefetch related when I know that many of the books will share the same publishers, and I'm working with a large query set because it will save Django from fetching the same publisher from the database again and again and again. And these issues, they are very important to find and to fix, but it's quite easy to find them during development using tools like Django Debug Toolbar, which can show you the number of queries a specific page takes. And there are tools like Sentry that can run in production and auto-detect them. Since a specific Sentry upgrade, I started getting emails, oh, we found an N+1 query in your code, do you want to fix that? And it's really helpful. But what if we've done all that and we've learned all that and the code looks good and it's executing the right number of queries and it's fine and fast and efficient in the development environment, but still slow in production? What most likely happened is that one of your queries is suddenly slower than when you tested it because of your growth and database size. But how do we figure out which of the queries it is if they're all slow in our Django Debug Toolbar locally? So there's many ways to do this. You can run Django Debug Toolbar in production only for admin users or stuff like that. I've come up with a different way that I quickly want to share with you. I try to replicate the request that the customer was complaining about in my browser with my session, with the access to the specific view. I open up my browser developer tools and I click copy as curl to get a string representation of the request with all the headers going into it. And I built a neat little tool that I've called Django debug request. It's a management command where I can just replace the curl at the beginning of the command with manage.py debug request. And what it does behind the scenes is it uses django.test.client to run the exact same request through the Django stack with debug mode enabled just for that one request. And it can print out all the queries it's doing and the timings that they have. So it's 20 lines of implementation of a management command, but it has changed how I debug things in production a lot. Now that I found the query, in this example, there's one that takes 50 milliseconds. Okay, that's not that much. And the other one, 128, it's not that much. But I can take one of the queries and I can ask my database for the query plan. We've also heard about query plans in the Q&A of Karen's talk this morning. I just prepend, explain, analyze, and the database will give me something like this. And as we've already established today, this is not an easy thing to read. So we're going to look at a few very specific examples of keywords to look out for, even if you haven't fully understood how to read a query plan. And to do so, let's back up a bit and talk about indexes. Indexes are this magic thing that makes your database go fast. But on closer look, indexes are not that magic. They're actually quite simple to understand. Indexes are basically specialized maps to your data. It's another table that your database manages for you, where it kind of inverses how the data is stored. So if we have an index on the publish date of our books, we have an additional table where for every publish date in order, we have a reference to all the books that have this publish date. And it makes both finding books with a specific publish date as well as sorting books by the publish date a lot easier for the database. So how do we figure out that we're missing an index? Let's work with a little bit simpler example of a query. We select all the fields from the book table. We have a join of our publisher, which is basically the select related that Django does for us. And then we filter all books where the title contains Lord of the Rings. And the upper function makes sure that the search is case insensitive. And the query plan for this looks like this, and we don't need to understand everything that's going on here, all the numbers and repetitions and loops and so on, but there are a few key phrases to look out for. One of them is sequential scan, abbreviated here to sec scan. And what it means is that the database is going through the entire table, row by row, and checking one by one, does the title fulfill my condition? And as you can see, it says rows removed by filter, 103,050 rows that the database needed to look at, even if they were not necessary for the result. Unsurprisingly, this is not very efficient at 100 milliseconds, and if we would have 1,000 times the rows on the table, I believe this would scale linearly, and we would be talking about a lot more time. So what can we do? We can add an index, which in this case would be a very specific index, a little bit more complex because we want to do a substring search. We would do a trigram index on the uppercase version of the title. We can define that in Django these days. And after we created that title, the most important thing to note about the query plan is that there's no longer a sequential scan going on there. Instead, there's one of the words that we like to see, which is an index scan. And the performance goes down from 100 milliseconds to about 3.6 milliseconds. So that's nice. Let's look at a second example of how we spot a missing index. If we modify the query a little bit, we say, again, select star from book. And in this case, we don't apply a filter, but we order by the publish date and limit to 100 books. So we want to see the 100 oldest books in our database. Then we see in the query plan that it is again doing some kind of sequential scan. It's fetching all the books from storage and then applies a sorting algorithm to it. So we see here it's heap sort, we don't care. What we do care a little about, it says memory. It uses 100 kilobytes of memory to do the sorting. And this is still good. If you ever see the word disk in a query plan, you should either very quickly start tuning your database or your queries, because you're going to be ending up in a very bad situation if the data size is too big that it's going to be able to handle this in memory. But we're not satisfied with the result here of 34 milliseconds. This is probably not linear in the dataset size, but still bad if it grows more. So what we can do is even simpler in this case. We just add db_index to our Django date field, and the query plan reduces to an index scan that takes 0.3 milliseconds. So again, a huge improvement. So let's add indexes everywhere. Oh wait, unfortunately, indexes do not come for free. Every index needs storage. Again, it's a table the database manages for you, basically. It needs to be saved somewhere. Also, it needs to be updated every time your dataset changes. So while you save time on select, you lose time on update, insert, and delete. And PostgreSQL comes with tools to find frequent sequential scans. So you might know which tables might use an index, and indexes that are rarely used. So you might consider to drop the index. However, as an application developer, I think these are nice, but I try not to rely on them too much. They tell me only about frequency, but I sometimes care about importance more than frequency. A query might be executed a lot, and I might still not care that it's a little bit slow, and a query might be executed only once per month, and I still care that it is fast. And these statistics will not be able to tell me these things. Also, which indexes to create is not always obvious, because while indexes are not magic, the query planner most certainly is. Let's look at the combined example of the previous two that we've seen. We select start from book. We don't filter by the title, we filter by a publisher instead. We want all books from publisher 42. We order them by how old they are and want to get the 100 oldest. So PostgreSQL now needs to decide, is it going to use the publisher ID index to very quickly fetch all books from publisher 42 and then sort them? Or is it going to use the publish date index to very quickly get the oldest books and figure out which ones are from publisher 42? So let's do a quick show of hands. Who thinks the database will use an index to speed up the publisher 42 query? Okay, who thinks it's going to use the publish date to sort quickly? Okay, very interesting. Who thinks we have no idea and we need to test it? Wonderful, that is the correct result. Interestingly, it uses the publisher ID index and then sorts the result if we do it with publisher 42. But if we do it with publisher 10, it goes the other way around. And it uses the index scan on the date and filters out. Turns out there are huge multinational publishers with thousands of books published, and there are small indie companies that publish just one book. And depending on which one you're dealing with, one is way faster than the other. So this is something we deal a lot with in our day-to-day projects, because we have very small and very big clients all in the same database. This is exactly what's happening to us all the time. The database needs to guess which way the query is going to be executed faster. And what if the query planner guesses badly? The option number one is to make sure it has some information to guess. Postgres will build a statistical model of your table to make good guesses. To build that model, you can run the analyze command. PostgreSQL should be doing this automatically, but if you don't have a DBA on your team, chances are your auto-vacuum process is not tuned properly, and you can try if that is the case by if you execute analyze and suddenly everything gets faster, you should be looking into tuning auto-vacuum. However, what we found also to be helpful in our case is to allow PostgreSQL to save more statistics. By default, it would look at 1,000 rows and then build a statistical model of your table based on that. We found for some of our tables, it is useful to just let it look at 10,000 rows instead and build a more in-depth statistical model. The second option is to look at specialized indexes, not only on a specific column, but on the query, based on the queries that we often need to do. For our case, we could define a combined index on the publish date and the publisher. And if we do that, PostgreSQL will decide that the quickest way is to use this specialized index, and our query time consistently goes down to a very small amount. There is a third option, and I'm very cautiously mentioning it. You can try to trick around the query planner, but it's hard because the query planner is really, really clever. Here, 3 times the same query and increasingly complex variations. The first is just select where order limit. The second is wrapping the where part in a subquery, and the third in a common table expression. And PostgreSQL, I think, starting version 12, is clever enough to figure out that these are all the same thing and will not be fooled by you trying to write a query and thinking you're clever, more clever than the database. In case you are very, very sure you are more clever than the database, you can tell it to do what you want it to do and do the one thing first. But I have seen maybe 1 or 2 situations in my career where this was an adequate solution, and even there, you could probably discuss about it. So usually try one of the other options, give your database the ability to collect more statistics, or figure out what indexes are actually useful to you. So let's move on to the second situation, where we know everything is slow, the database uses a lot of CPU time or disk bandwidth or whatever, and all our users are suffering because the application is slow, but we don't really know why. And the first thing we do in a situation like this is we check, do we just have high incoming load? Do we have thousands of people trying to access our site at the same time? And if we do, it's probably not a problem with our code or not one specific problem we can easily find and fix. It's just that we need to optimize generally or get more server power or whatever. But sometimes a single feature creates so much load on the database that everything slows down just because one query is being executed a lot. So what we do first is we look on the database directly for long-running queries. PostgreSQL can tell you which queries are currently running and for how long they've been running. And in my experience, if you execute that statement a few times in a row over a few minutes and just look at the results with your eyes, you will see the same query running for 10, 20 seconds over and over again, and it will be obvious which query is causing the problem. It is usually less obvious to then figure out which part of your Django code is generating that query, but I have not found a quicker way than knowing your code base very well to work around that. Maybe someone has ideas to share there. If you want to do this in a more scientific way than looking at the output 5 times, there's pgstat statements, a Postgres extension that can collect statistics about which queries are running how often and how long they take. And again, there's tools in Django level like Sentry that we use that can proactively look at performance data of specific queries and where they are coming from. In the third situation, and then of course repeat the same process that we had in the first situation where we already knew where the issue was. Occasionally though, the application starts to get slow or is slower than we would like it to be under load, but the bottleneck is not the database. So we need to figure out which resource is the bottleneck. And ideally we have some kind of instrumentation in place to look at statistics of our machines, and we can look, is it the memory, is it the CPU power, I've seen our application to be constrained on network bandwidth before. But with Django applications, I'm going to bet you 95% it is the CPU power. Because Django applications, if you don't screw up too much, usually don't leak memory too much. They usually have rather constant memory profile once they're running. Network bandwidth is rarely the issue. Usually you're using up more CPU time than you have. And we've been talking about profilers today as well already. And my favorite one for a number of years is PySpy. PySpy, unlike cprofile, which runs in the Python process and runs the process in a different way, PySpy is a sampling profiler that attaches to a running process. You can do that in your development environment, but you can also attach to a running production process without needing to start the process. You can SSH into your server, install PySpy, and point PySpy to one of your Unicorn or UWhiskey worker threads and collect profiling information for a few minutes. And unlike cprofile as well, it gives you actual trace specs, and it can provide a very nice heat chart like this, where you can look into the specific code paths your application is spending a lot of time in. Now, when pointing this at a production Unicorn worker, you need to filter out a few things where it says, okay, I'm spending a lot of time waiting for the next requests. That is fine, and should be spending a lot of time there. But there are many other things, and you will see a lot of Django template engine taking up a lot of time. There's probably not so much you can do about that in many situations. But we found the most interesting things. For example, we use Django countries, a package that allows us to render a country selection box for an address. And Django countries does this very well. It gives an alphabetical list, and it is localized. And it uses a Unicode-aware sorting algorithm to alphabeticalize the list of countries. And this Unicode-aware sorting is surprisingly slow. So on a page where we have 10 address forms, this became a major performance issue for us, that it was sorting the list of countries 10 times to render that page. So we introduced caching for our usage of Django countries. I don't think we would have ever found that performance issue without a tool like PySpy. So this has been a quick 22-minute look into the toolbox I open when we deal with performance issues that are happening suddenly and without a specific optimization plan, but often under a lot of stress, and we need to fix this today or someone will be very unhappy. And I hope that maybe some of these tools have been new to you and will be helpful in making your applications go faster. And I believe that's the end, and we will have some time for questions before the coffee break.